Hey there, and welcome to The Explainer. Today we're tackling a surprisingly tough stock market problem. And believe it or not, the key to solving it is something you've seen 1,000 times in a cafeteria. Yep, we're talking about the simple, elegant power of a stack.
I know, it sounds a little weird, right? Plates and stock prices, but stick with me because by the end of this, you're going to see exactly how that simple stacking logic can make a super complex calculation not just doable, but lightning fast. All right, let's get into it.
Okay, so first things first, let's lay out the puzzle. Picture this, you're a stock analyst. You've got this massive spreadsheet in front of you, just rows and rows of daily stock prices. And your job? For every single day, you need to figure out this one specific number, a metric called the stock span.
So what on earth is a stock span? Well, it's pretty simple. For any day you pick, you just look backwards and you count. You count how many days in a row, including today, the stock price was the same or lower than today's price. As soon as you hit a day that was higher, the streak is broken. That unbroken chain of days, that's your span.
Let's make this real with an example. So, look here at day 5. The price is 6. Now, we look back. Day 4, day 3, day 2, all of their prices are lower than 6. So we count them up. 1, 2, 3, and day 5 itself makes 4. Boom. The span for day 5 is 4. See? Easy enough for just one day. But what happens when you have to do this for years of data? That's where it gets tricky.
All right, so the first thought, the totally obvious way to solve this, is to just, do exactly what we just did, but with code. For every single day, you tell the computer, start a counter. Now loop backwards, day by day, and keep counting until you hit a price that's higher. It makes perfect sense, right? It's logical, it's intuitive, and hey, it'll get you the correct answer. But, and this is a big but, there's a huge catch. And here's the catch. This method is just painfully slow. In the world of computer science, we call its performance O of n squared, or n squared. And what that really means is that the work doesn't just grow, it explodes. So for, say, 100 days of data, you're doing around 10,000 calculations. Okay, maybe not so bad. But for a year, you're already over 100,000. And for a decade of stock data, we're talking more than 13 million operations. It just falls apart. It doesn't scale for the real world. We need a much smarter way to do this. And that smarter way? It comes from this beautiful, simple idea in computer science, something based on a principle called last in, first out. So it's time to meet the hero of our story, the stack.
So what is a stack? It's nothing fancy, really. It's just a list of things where you have one simple rule. You can only add stuff to the top, and you can only take stuff from the top. That's it. So the very last thing you put in is always the very first thing you take out. And that gives us the acronym LIFO, last in, first out.
And honestly, the best way to picture this is with that cafeteria analogy. You walk up to a stack of plates. Where do you take a plate from? The top, right? You'd never try to wiggle one out from the middle or the bottom. And when a new clean plate is added, where does it go? Right on top. That physical stack of plates is a stack. The last place placed on top is the first one taken. It's that simple. Now, to actually use a stack in code, we only need 3 basic moves. When we add an item to the top, we call that a push. When we take the top item off, that's a pop. And if we just want to look at what's on top without removing it, we call that top or peek. And that's really it. Push, pop, and top. With just those 3 simple commands, we're going to crack our stock span puzzle wide open. Okay, theory time is over. Let's actually put this thing to work. So how in the world does this last in, first out idea give us such a huge speed boost? Well, it all boils down to one really clever change in how we look at the problem. And this right here, this is the aha moment. Instead of looking back and counting every single day over and over again, what if we just asked a different question? What if we only cared about finding the closest previous day where the price was higher? Think about it. That's the day that breaks our streak. If we can find that one day quickly, then our span is just the distance between today and that breaker day. The problem becomes way simpler. And that is the job we're going to give our stack. As we go through our stock prices day by day, the stack is going to be our smart little helper. It's going to keep track of some of the previous days for us. But here's the clever part. It doesn't keep track of all of them. It only holds on to the days that create a line of increasing prices. It basically acts as a filter, throwing away all the useless lower price days that we don't need to worry about anymore. So here's the play-by-play. Check it out. We start with a totally empty stack. We look at day 1. Then for each new day, we look at the top of our stack, and we ask a simple question. Is today's price higher than the price of the day on top of the stack? If the answer is yes, then that day on the stack is totally irrelevant now, right? It can't possibly break a future streak because we just found a day that's both higher and closer. So we pop it off, get rid of it. We keep popping off these now useless days until the day on top has a price that's actually higher than our current day's price. That day, that's our streak breaker. We calculate the span and then, for the final step, we push our current day onto the stack. It now sits there, waiting to see if it will be the streak breaker for some day in the future. So what's the payoff for all this clever pushing and popping? We go from that awful ON squared to just ON. And that isn't a small step up, that is a giant leap. Our first method was grinding to a halt with millions of steps. This new one? Its work grows in a straight line with the number of days. It's a game changer. And why is it so fast? Because every single day gets pushed onto the stack exactly one time, and it gets popped off at most one time. All the work is spread out perfectly. It's just so much more efficient.
Okay, but let's get practical for a second. Usually, when you build a stack, you use something simple like an array. But arrays have a fixed size. So you might say, okay, I'll make space for 1,000 items. But what happens on day 1001? What happens when your data is bigger than you expected?
Yeah, this is a classic programming headache. If the stack gets full, your program just stops. You get an error and it all comes crashing down. So we need a plan. We need a strategy to let our stack grow on demand, especially when we don't know how much data we're gonna get.
And really, there are two ways to handle this. The first one you might call the tight strategy. When you run out of room, you just add a little more space, like 4 or 5 more slots. It feels safe, right? But you end up having to resize all the time, and that's slow. The other way is the growth strategy. This one's way more aggressive. When you run out of room, you just double the entire size of your array. It might seem wasteful at first, but think about it. You have to do these big, slow resizing operations way less often, and that makes a huge difference.
And when you run the numbers, there's no contest. That growth strategy, doubling the size, is just clearly the better way to go. It keeps the average cost of adding an item super low, which means our whole algorithm stays fast and efficient. It's just another one of those cool, kind of counterintuitive moments where being bold actually pays off in performance.
Okay, so let's take a step back and look at the big picture. What did we really learn here today? Because this isn't just about stocks, and it's not even just about stacks. It's about something bigger, the incredible advantage you get from thinking algorithmically.
So here are the big takeaways. First, a really simple tool, a simple data structure, can absolutely crack a complex problem. Second, the obvious way to solve something isn't always the best way. In fact, it's often the slowest. Third, how you organize your data has a direct, massive impact on performance. And finally, choosing the right algorithm, like going from n squared to n, isn't just a minor tweak. It's the difference between something that works in theory and something that works in the real world.
And that kind of leaves us with one last question to chew on. The stock span problem. It seemed really tough at first, but then the right tool, the stack, made it almost trivial. It really makes you wonder, doesn't it? What other huge, complicated problems out there, in science, in business, wherever, are just one clever, simple data structure away from a beautiful, elegant solution? Thanks for joining me.